Do you guys kind of feel her concern? Her concern is that I'm not necessarily going to get an upper estimate or a lower estimate. That's what you're worried about, right? I totally agree. Fortunately, and I feel like this feels right, we're going to talk about this more in like 10 minutes, by letting my number of rectangles go to infinity, it sort of just all doesn't matter, right? Because I'm going to have so many rectangles that in fact what I'm going to end up with is the exact answer. Does that feel right? Alright, more on this in a minute. Okay, let's do this problem. What is the area? I'll go kind of a little bit faster now. The first rectangle is going to have width 2 over n and height. Well, the height of the first rectangle is f of that point. In other words, it's going to be f of -1 plus 1 times 2 over n. The height of the second or the area of the second rectangle is going to be the width of the second rectangle times the height of the second rectangle, which is f of -1 plus 2 times 2 over n. And now I'll just throw in some dots, and we'll say the nth rectangle is going to have area, the width of the nth rectangle times the height, which is -1 plus n times 2 over n. And now, I think I'm ready to write this in sigma notation. It's going to be 2 over n times the sum from I equals 1 to n of f of -1 plus I times 2 over n. So the thing that's changing each time is like that number. Okay, raise your hand if you got this far. Alright, good. This to me is the important step. This means that you understand what you're actually doing. You've thought about the problem correctly, you've made a picture, you've processed all the areas, and you understand actually what you're doing. Now it's just a matter of, we just have to crank it out, right? So let's do it. So we get 2 over n times, and now what do I have to do now? Only one thing to do. Plug it into the, first I have to plug it into the function. So I have to plug into the function -1 plus I times 2 over n. So it's going to get a little ugly, right? It's going to be 2 over ni minus 1 squared minus 2 over ni minus 1 cubed. And in my opinion, you should try to just simplify as much as you possibly can inside the brackets, combine all like terms, and then get the answer. So let's keep going. So I have 2 over n on the outside times the sum from I equals 1 to n of, and now I'm gonna, well, I guess this one I can just do because I know algebra 1. It's gonna be 4 over n squared I squared minus 4 over n I, yeah, plus 1. And now here you have some options. You can either do it out or you can use the binomial theorem. I think I'll use the binomial. Should I use the binomial theorem? I don't know. Let's see if I can use the binomial theorem correctly. So it's the first one cubed. So it's going to be, or I could have, well, okay. So it's 8 over n cubed I cubed minus, and then it's going to be 3 times that one squared times that one, right? So 3 times, if you do that one squared, you're going to get 12 over n squared I squared. You guys following this? Is this what most of you did? Who got it right? You did the binomial theorem?
I squared.
What did I forget? Squared. And now it's going to be plus 3 times that one squared. So that's going to be 6 over ni plus 1. Get it? Right, so that's just algebra. If you didn't want to use the binomial theorem, you could have just done it out in multiple steps. All right, and now I am going to, because I feel like this is easier, I am going to, inside the brackets, recombine everything into like terms. So I have -8 over n cubed I cubed. Then the squares, I'm going to have, I guess, plus 16 over n squared I squared. Then here I'm going to have a minus 6, so that ends up as minus 10 over ni. And then the plus 1 cancels the minus 1. What's up? Ah, man. That's a minus 1. So 1 minus, so this is going to be plus 2. Okay. Alright, so with Laura's help twice, I now have a correct, I basically just expanded that polynomial correctly. Those of you who got messed up, was it around here that the error was made? No, yes. Feel free to give me some feedback. Alright, whatever. Moving on. Now, what do I do? I think now I'm going to split it up into a whole bunch of different sigmas. So I get negative.
You could also take out the 2.
I could, but I'm just going to do it. So I get negative 16 over n to the 4th times the sum from I equals 1 to n of I cubed plus 32 over n cubed sum I equals 1 to n I squared minus 20 over n squared sum I equals 1 to n of I plus 4 over n sum I equals 1 to n of 1. Now that I've done all of that, I'm ready to apply my formulas. So this formula, as we reviewed last class, is n squared n plus 1 squared over 4. This formula is n plus 1 2n plus 1 over 6. This is n plus 1 over 2, and this is going to be just n. Avery, you getting all this?
Yeah.
Okay, now you just have to do lots of little like fraction moves. Let's try to be careful. The n squared cancels at 4, and that becomes an n squared. The 4 kills that 16. This is, I can take a 2 out of the top and bottom, so that's 16. You can take one of those n's out. Here, can kill one of those n's, and that's a 10, and then that. Okay, yikes. So, this is going to be negative 4 times n plus 1 squared over n squared plus, I have 16 thirds times, and just to remind me, I'm going to multiply out that numerator because it's 2n squared plus 3n plus 1 over n squared minus 10 times n plus 1 over n plus 4. Yikes.
No, it's 2n plus.
So, this expression in terms of n represents the area under this curve from negative 1 to 1 as approximated using Rem with n rectangles. And what we now want to do is take as many rectangles as possible. We put in all this hard work to do n in general, so let's let n be like a billion. Let n be a billion, we're going to get a really, really good approximation of this area. The more rectangles we have, the skinnier they are, the less error we're going to get. And if we just take, and this is sort of the concept of the limit is what's linking these two halves of calculus. If we take the limit as n goes to infinity, we're saying let there be an infinite number of rectangles. And it's just quite amazing, I think. All right, so what happens? I get negative 4, that's just 1, plus 16 thirds. That polynomial goes to 2, right? Minus 10 times 1 plus 4. And hopefully, if I'm doing this right, this should be the answer. The 4's cancel, and I get 32 thirds. No.
Yeah, that's
Yeah.
right.
Yeah.
32 thirds minus 10?
Yeah.
Oh, yeah. 32 thirds minus 10, so minus 30 thirds, and the answer is 2 thirds. All right, yes, good. Round of applause for math. Those of you who got messed up, where did you get messed up? Jeff G, did you get the right answer? On the algebra, like around here somewhere? Yeah, you need more practice. Brooke, did you get this right? Where'd you mess up?
Converting it to add.
Converting it to, like down here? Yeah. Okay. Christine Cho. Algebra. Okay, good. This one's pretty much hard to get. Okay, can I have this homework? Before I do, let's do a couple shout outs. We gotta do like 6. Let's go, fast. Do it, what do you got?
Shout out to Ben.
Alright, good. Give me your card when you're done. Crab, what do you got?
Shout out to Jacob Santangelo for being the coolest Santangelo I know.
Alright. Who else? Who'd you have? No one. Who do you got?
Shout out to Ray Wang, tallest person I know. Oh yeah, Ray.
Okay, good. Let's do a couple more. Let's go. Alright, Elijah, what do you got?
Ryan Holland is trash at NBA 2K.
Ooh. Anyone else on this table? We're all done? Let's do this table. He's gonna actually be here, but he's not gonna be watching the video, but just trash him anyway. No, just shout out to him. I mean, we can say something positive. Chill, calm.
David Hines, were you at a prom with me?
Awesome.
Shout out to Marissa and her SPF 100 sunscreen.
Okay, cool.
Shout out to Serena, one half of the cutest couple in period 3. Serena and Euro.
Okay, good. Let's let's hand in the homework. Let's turn it in like right here. We sit there? No, right there.
Hey, no problem.
Allocation. Too old.
Yeah.
Oh my god, they really inspired me.
Oh, wait.
Mine are better.
Alright, good. We are now gonna do something that's kind of hard, and it might fail, so that'll be fun. Let's do it. So, take the following bundle. F of x equals root x. And we want to do this on the interval 0, 1. And I would like to find the area under this curve. Go. In principle, this is exactly like what we just did a minute ago, but there's a tiny bit of a difference, and you may see the danger coming, and you may not see the danger until it is already upon you. So same old, you know, we want to find the area under the curve. How many rectangles should we use? N rectangles. Let's use RM. That seems to have worked for us in the past. Okay, so just jump in, and then when you get to a bad spot, start crying.
Okay.
Start crying.
Why not? Can I make
That's what it looks like. Oh wow.
So draw a picture. This is the area that I want, right? Yeah, some of you are getting kind of sophisticated. You don't even need to draw the picture, so you think. Okay.
That's ominous.
So if we're using n rectangles, what's the width of each rectangle?
1 over n.
Yeah. So delta x is 1 over n. So that's 1 over n, 2 over n, 3 over n, 4 over n, etc. And then you could start labeling these coordinates. What's that point right there? I guess it's going to be 1 over n comma f of that. And the next one will be like 2 times 1 over n comma f of that. 3 times 1 over n comma f of that. Drag them all up. So maybe I'll just go right to the sigma. Is that okay with you guys? Because we're getting more experienced. So if we go right to sigma, it's going to be the sum from I equals 1 to n of the width of each rectangle is 1 over n, and the height of each rectangle is f of I times 1 over n. Who got that? Okay, that's like most everyone who was going fast got that far. Okay, but then I don't see any of you crying. Was this the class where I cried on demand last semester? Who was there in that room? I think I might have done it in logic. Logic. I said, yeah, I'm not going to do it right now, but I learned that I do have the ability to do that. I just decided one day to do it. Cry on demand, and I just did it. No, there are far more. This is not even in the top 10 of challenges we faced in the coming weeks. Okay, so this is 1 over n times, well, f is just the square root, so what I end up with is the square root of I over n.
Oh no, what the heck?
Yeah.
It's about one more thing I could do, I guess, because I can use, I could factor out some stuff. I could take out like a 1 over n root n. That's like legit. And then, all right. So here I am, and now I cry. Because why am I crying? Yeah, I simply am stuck. I do not know how to proceed because I do not have a formula for the sum of the square roots, right? I know of no formula, we certainly didn't do it in pre-calc C, for what is going to be 1 plus root 2 plus root 3 plus root 4 plus root 5. And it doesn't seem like that formula is going to be very nice, if it even exists at all, right? So I'm stuck. And pause. This actually reveals that though I had boldly claimed to solve the area problem, what have I really solved the area problem for? Polynomials, yeah. As I we should, oh yeah, or we could just do polynomials and we could just deny the existence of any other function. That's actually not so extreme as it might sound. But wait, hold on, stay focused. It turns out that I can do that. I can now find the area of any polynomial. But if it's not a polynomial, I'm kind of screwed. For example, if you want to find the area under sine, good luck. I don't have a sigma formula for that either, right? So there's more going on here. Okay, how can I solve this? All right. Well, here comes a solution. And it's not a solution that I necessarily would have thought of myself. It's in the book. So it goes like this. Ready? What we are going to do is we are going to use rectangles of unequal widths. Okay. And this is motivated by the following idea. The motivation here is, look, I have this square root, right? And something needs to go away. If it doesn't go away, I can't do anything. So what makes square roots go away? Squares. Yeah, so what I'm now going to do is I'm going to change everything around in such a way that I only ever plug perfect squares into this formula. What is right? Okay, so watch this and just behold the amazing, coolest idea ever of this. I'm going to let on my first rectangle, is going to be at 1 over n squared. My next rectangle is going to be at 4 over n squared. My next rectangle is going to be at 9 over n squared. And dot dot dot, my last rectangle, whose width is going to not look totally right because I ran out of space, is going to be at n squared over n squared. In other words, I am going to set this system up in such a way that I sample the height of the function only at perfect square points, so that when I go to plug them into this function, I get like nice numbers. Okay, but what's going on? This just seems weird, right? Because now, Sabrina, all my rectangles are going to be of all different widths. So let's talk about that. Is that okay? I don't know. What's going on? All right, so a couple of things. So some people call this little point C. So let's just call it that. So C sub 1 is this first place, 1 over n squared. C sub 2 is 4 over n squared. C sub 3 is 9 over n squared. And in general, what is C sub I? The right-hand endpoint of the ith subinterval.
I squared over n squared.
I squared over n squared. Excellent. Okay, good. So I'll even write that. This is the right endpoint of ith subinterval. Okay.
Wait, isn't it I squared over n to the? Oh wait, never mind.
I think that's right. Yeah. Okay. So next is I mentioned that these rectangles all have different widths. So let's see what those different widths are. What is delta? Oh, I can't call it delta x anymore, right? I have to call it something weirder, like delta x1. So delta x sub 1 is the width of the first rectangle, the first subinterval. And what is it?
C sub I minus C sub 0.
Oh, you're giving me a formula in general. Let's just one step at a time. The first one has width, everyone? 1 over n squared. What's delta x sub 2? That's the width of the second rectangle. Everyone look at the picture. What's that width? Yeah, okay, again, you're trying to be cool about it. It's just 3 over n squared. What's the width of the third one?
5 over n squared.
5 over n squared. And now, Prem, would you like to conjecture a formula for the width of the ith subinterval?
I over n squared. Plus, wait, no.
What are those numbers in the numerator? Those are like the odds, right? So what's the pattern for the next? It's like 2i minus 1 or something. I think that works, right? Yeah, 1, 2, 3. Yep, over n squared. So I think that's right. If we want to check to be sure that that's true, what could we do? We could actually compute it. This is what he was saying, right? In general, delta x sub I should be, by definition, what?
C sub I minus C sub I.
Yeah, good. It's C sub I, the right-hand endpoint of the ith subinterval, minus C sub I minus 1, the right-hand endpoint of the previous subinterval, which is also the left-hand endpoint. Is everyone feeling this? Right? This is the right endpoint, and this is the left endpoint of the ith subinterval. Okay, and now just doing math, as we define C sub I to be I squared over n squared, this is I squared over n squared minus, this would be I minus 1 squared over n squared. And if we do that subtraction, what do we end up with?
2i
We-
minus 1 over n squared.
We end up with that, right? I squared minus 1, so yeah, we get 2i minus 1 over n squared. So indeed, we have just proven that the ith subinterval has this kind of width. Okay, why is that? Okay, so what is there to say about this? Well, This is strange, but maybe not so bad. Because as n goes to infinity, what's happening? It's a little bit of a vague question. Let's call on a person. Michaela. No, you talk all the time. Tiffany. As n goes to infinity, what's happening? Where's Tiffany? There's 5 things happening, so you just need to tell me one of them. What happens as n goes to infinity? What gets bigger? N gets bigger. Okay, good. Let's take something a little bit better than that. As n goes to infinity, tell me one thing that's happening as n goes to infinity. I don't know. Like, what's happening to the rectangles?
You get wider.
Wait.
Bigger, more square.
The part gets bigger. Wait, this is complicated enough that I want to have a real conversation. Someone, what happens as n goes to infinity?
They get like.
There are more rectangles. That's one thing that's worth mentioning. That there are more and more rectangles, right? As n goes to infinity, there's more and more and more of them. Yet, yeah?
They become more and more like lines.
They become thinner and thinner because there are more and more of them. So actually, even though these rectangles are of unequal widths, if you hold n constant for a moment, then the rectangles get bigger and bigger as you move out, right? Each of these rectangles is wider than the one before it. Yet, as n goes to infinity, they're all getting pretty small. So maybe the fact that they're of all different widths doesn't matter because they're all getting small. And in fact, I can make that concept precise, right? As n goes to infinity, what is happening to delta x sub I? What is delta x sub I? It's that, right? It's this 2i minus 1 over n squared. What happens to 2i minus 1 over n squared as n goes to infinity? It goes to 0. And perhaps even more convincingly, let's take the widest subinterval. Which is the widest subinterval?
The last one.
The last one, right? The last one is the widest. So as n go, and then what is, maybe we could just do that. What is the formula? What is delta x sub n? What's the formula for the widest rectangle?
Thanks.
It's just going to be 2n minus 1 over n squared, coming right from that. So as n goes to infinity, delta x sub n goes to 0. In other words, even the widest subinterval goes to 0. Okay, since this is true, I'm going to call this okay. And now, if you didn't appreciate this before, you will now. What is the beauty of having set it up this way? Well, now when I go to find the area, I say that I'm going to take the sum of, well, let's put here the area of the ith rectangle. What's the area of the ith rectangle? It's the width. What's the width of the ith rectangle? We can maybe I'll just write it as delta x sub I, right? And then what's the height of the ith rectangle? F of c sub I. So in its most general form, the area of the ith rectangle is going to be the width of the ith rectangle times the height of the ith rectangle. Is everyone okay with that? All right, and then we go to plug this into the formula. This becomes, we're taking the sum from I equals 1 to n, and delta x sub I is that, 2i minus 1 over n squared. And what's f of c sub I? Well, that's going to be the square root of I squared over n squared. And by only plugging perfect squares into this formula, this now turns out to be something I know how to do, right? This is just going to be, you guys with me? Okay, so it's 2i minus 1 times I over n squared times n. And now, can we just do this really fast? This is going to be 1 over n cubed times the sum from I equals 1 to n of 2i squared minus I. Did I do that right? Yeah. And now this is something I know how to do using the old techniques. Everyone okay? Okay, I'm trying to kind of look a little bit rushed. So this is going to be 2 over n cubed times the sum from I equals 1 to n of I squared minus 1 over n cubed times the sum from I equals 1 to n of I. And from here we know what to do. This is 2 over n cubed times times n plus 1, 2n plus 1 over 6, minus 1 over n cubed times n plus 1 over 2. Do we have an answer? That kills that. Kills that. We're going to have a third times 2n squared plus 3n plus 1 squared minus
2n squared.
Squared. But anyway, this dies, right? And what do we end up with? 2/3. Yeah, which actually looks about right? Because doesn't that thing look like it's living in a box? It is living in a box, a 1 by 1 box. We just learned something kind of deep, which is that the square root function takes up 2/3 of that box. And actually, some years this happens, but I was going so fast I didn't really give anyone time to talk. But does anyone think that there was maybe another way we could have gotten around this whole problem? Yeah, Ryan.
So it's the inverse of x squared. So you could have just done x squared and then like subtracted it from 1.
Yeah. Ryan says that is the area under x squared from 0 to 1, which I just learned is 1/3. I didn't know that already. Cool? Okay. Good. That whole thing was meant to introduce you to the idea of rectangles of unequal widths. Somehow, I'm 40 minutes behind. Okay. Okay, good. Okay, let's do this now in general. In general, this is the kind of setup, and we talked about this. Jillian brought this up. The difference between using LRAM and RRAM, and maybe since we already talked about it, maybe it'll kind of go a little bit fast, right? So suppose you have some function, and you want to know the area underneath this function from A to B. So I'm going to try to draw the same function twice. That looks roughly the same. Okay, so we want to know the area under this curve from A to B. So first I'll lightly sketch it in green.